So imagine you spend, like, your entire life mapping out an island.
Okay.
You know every single rock, you know every coastline, every tree.
Mm.
And to you, it feels like this totally, complete, isolated universe, right?
Right.
But then one day, the ocean just completely drains away.
It vanishes.
Exactly. And you look down from what used to be your coastline, and you realize your little isolated island is actually just the tip of this massive, interconnected underwater mountain range.
That is a great visual.
Yeah. And the terrain beneath the water connects your home to, like, whole continents and landscapes you never even knew existed. And I bring this up because for centuries, mathematicians have essentially been trapped on these isolated islands. You know,
Oh, absolutely. I mean, it's a profound realization when you really look at modern mathematics.
Right.
You have number theory operating by its own very specific rules over in one corner.
Yep.
And then you have differential manifolds in another, and algebraic rings somewhere else entirely.
And they seem completely disconnected.
Totally autonomous. Yet, mysteriously, someone will make this huge breakthrough in a completely isolated field-like algebraic geometry, for example, and suddenly it dictates the absolute rules over in number theory.
Which is wild.
It is. Because that shouldn't happen if these are truly separate islands, right?
Right. Which brings us to the source material for today's deep dive. We are exploring a fascinating 2026 foundational text by Philip Lilien.
Yes.
It's titled Closure Mathematics, the Generative Architecture of Mathematical Domains.
A very heavy title.
Very heavy. But the mission for this deep dive for you listening today is to explore what Lilien calls a radical foundational inversion.
Yeah, that's the key term.
So we aren't just looking at, like, the daily mechanics of how math works. We are diving all the way to the bottom of that drained ocean.
Yeah.
To look at the generative engine, that single mountain range that actually creates all of mathematics.
Right, because the standard approach in mathematics has historically been, well, cumulative.
Like piling things up.
Exactly. We treat the field like this sprawling museum where we just keep adding new wings to the building.
Right, like, oh, here's the algebra wing.
And let's bolt on the topology wing over here. But Lillien's work forces a complete reorientation of that.
How so?
He argues that we have to stop treating math as this historical accumulation of disconnected domains. We have to identify the common source from which they all necessarily emerge.
And that single source, right, the underwater mountain range connecting everything, Lilien calls that closure.
Yes, closure.
But I want to set some expectations for you right now, because this is not the concept of closure you might vaguely remember from, like, your high school math class.
Oh, far from it. Not at all.
Because in standard education, closure is usually taught as a really localized property, right?
Right. A teacher will stand up and explain that the set of integers is closed under addition.
Because if you add two integers, you just get another integer.
Exactly. And in that context, closure is merely this technical condition operating inside a domain that has already been built for you.
The sandbox is already there.
Yes, the domain comes first, and closure is just the localized rule playing out within it.
Right, you already have the sandbox of integers, and closure is just, one of the games you're allowed to play inside it.
Exactly.
But Lilien makes this claim that just flips this entirely on its head.
He really does.
He states that closure is not a property within mathematical domains. It's actually the primitive, generative principle from which those domains arise in the first place.
Domains don't ground closure.
Yeah.
Closure grounds domains.
Okay, that is a huge shift. So to really grasp this foundational inversion, we have to look at his primitive definition of closure.
Right. And he defines closure as the principle by which a regime of mathematical determination preserves or completes itself under its own admissible mode of formation.
Okay, that's a mouthful.
It is. But at its absolute most primitive level, closure is just the condition of determinacy.
So let me try to unpack determinacy for a second, because that sounds a bit abstract.
Sure.
If I don't have closure, what am I actually looking at? Is it just chaos, like static on an old television set?
Static is actually an interesting way to visualize it.
Really?
Yeah. Think of determinacy as the absolute prerequisite for identity and stability.
Okay.
Without closure, any mathematical operation or relation you try to attempt doesn't remain within a coherent regime. It just doesn't stabilize.
It just falls apart.
Right. If you lack closure, there's no structural difference between a lawful, logical continuation and just a completely arbitrary departure.
Like random noise.
Exactly. You wouldn't be able to distinguish a rule from random noise. Closure is the primitive condition under which a formal system becomes possible at all.
Wow.
Yeah, if a regime lacks closure, its admissible operations immediately dissolve its own identity.
So if we take traditional foundations like set theory or category theory, usually mathematicians take a domain, like logic or sets, and they ask how other structures can be built or represented inside it.
Right, that's the standard way, yes.
But Lilien is arguing that we have to step even further back. We have to begin with a condition under which any domain becomes stable enough to hold laws in the first place.
And that is the core of the foundational inversion. Closure is prior in the order of intelligibility.
Okay.
What we commonly refer to as a domain, like arithmetic or geometry, is actually just a specific stabilized expression of closure.
Got it.
Lilien terms these closure regimes.
Closure regime.
Right. A closure regime is simply a structured mode where closure is realized with enough stability to actually support a distinct mathematical reality.
You know, it makes me think of like water taking different physical states depending on the environment.
Oh, I like that.
Like it can manifest as solid ice or liquid water or gaseous steam depending on the temperature and pressure.
Yes.
So the mathematical domains, algebra, topology, calculus, they're the ice in the steam.
Exactly.
But the underlying closure is the H2O molecules themselves, generating those forms based on how stable the environment is.
Let's push that analogy even further because the mechanism is what really matters here.
Okay, push it.
It's not just that water changes form. It's that the internal laws governing the molecules dictate those forms.
Right.
Mathematical lawfulness isn't just a set of arbitrary rules imposed from the outside by some mathematician writing on a chalkboard.
It's not invented.
No. The law arises from the intrinsic regularity of the closure regime itself. The emergence of a mathematical law is just a regional expression of closure achieving stability.
Okay, so if closure is this ultimate generator, right, the H2O, the mathematical universe, we have to figure out what it generates first.
We do.
We have to go down to the absolute base of the architecture, where closure operates at its most raw, unmediated scale.
Right down to the bedrock.
Exactly. And that leads us to the first manifestation, which he calls discrete closure.
Right. When mathematical domains emerge as closure regimes, we inherently have to start with the regime where closure appears in its most immediate form.
Which is what?
In discrete closure, stability is realized through exact bounded admissibility.
Which gives us the birth of number, like the foundation of arithmetic.
Exactly. Number is the first stable realization of closure.
Okay.
In a discrete regime, identity is preserved through separation. Lilien defines this by stating that a regime exhibits discrete closure when its admissible formations preserve identity through separation and proceed by exact recurrence among distinct units.
So identity by separation, this means units have to essentially hold their ground, right?
Yes.
They don't fuse together, they don't overlap, there's no gray area.
None at all. The mechanism requires three very specific structural ingredients to function.
What are they?
First, you need separation. The units must absolutely refuse to melt into one another.
Okay, separation.
Second, you need recurrence. The formation must be able to continue lawfully, step by step.
Right.
And third, exactness. Each step must be absolutely determinate without any fuzziness or approximation.
Let me test an analogy here just to make sure I'm getting
Go
that.
for it.
I initially thought of this like laying bricks to build a wall. You can distinctly point to the first brick, then the next brick, and the next. The separation is what creates the structure.
Sure.
But a brick can be chipped or mortared together. So maybe a better way to look at it might be digital bits in a computer's memory.
Oh, that's much better.
Right, because a bit is either a 0 or a 1. It occupies a totally distinct state.
Yes.
If the bits started bleeding into each other, like if a 1 became a 0.8 and smeared into the next bit, the entire digital architecture would instantly collapse.
Completely.
So the non-collapse of the unit is what generates the arithmetic form.
The digital bit analogy captures the necessity of exactness perfectly.
Nice.
Lilien actually provides a rigorous proof for this exact separation condition.
Oh, he does, yeah.
He shows that if units fail to remain entirely distinguishable, exact stepwise recurrence becomes completely impossible.
Because the transition from one to the next just gets blurry.
Exactly. The transition loses its definition. Identity in a discrete regime is fundamentally secured not by how units interact with each other, but purely by their rigid separation from each other.
Okay, and this rigid separation brings us to the ontological roles of 0 and unity.
Yes.
Now, for most of our lives, we just treat 0 as a placeholder for nothing and 1 as something.
Right, just basic counting.
But under closure mathematics, they are the structural pillars holding up this entire first regime.
They really are.
Lilien defines 0 as the absolute baseline of admissibility. It is the state where recurrence is possible, but hasn't actually happened yet.
Exactly. And unity is defined as the first positive, stabilized, discrete act.
Okay.
You need both of these to form the minimal structural polarity required for arithmetic to even exist.
To even get off the ground.
Right. Without the baseline of 0, there is no grounded regime for succession to initiate from.
Right.
And without the stabilized, discrete act of unity, recurrence remains dormant. It never becomes a positive formation.
I had to pause here, though, because there's a serious friction point for me.
What's that?
Well, when we learn math as toddlers, the very first thing we do is count.
Sure.
We count our fingers, we count little wooden blocks. It feels incredibly intuitive.
Of course.
We don't sit in preschool contemplating baseline admissibility and stabilized discrete acts. So isn't counting the true primitive foundation of math?
I mean, it feels primitive because of how human cognition develops, but structurally, Lilien demonstrates that counting is entirely derivative.
Wait, counting is derivative. That is a massive paradigm shift.
Think about the mechanics of what you are actually doing when you count.
Okay.
You are iterating. Counting presupposes that discrete closure is already firmly in place.
Oh, I see.
You cannot point to a sequence of wooden blocks and assign them numbers unless those distinct units are already perfectly stable and absolutely refusing to collapse into each other.
Right.
Counting is just the finite or indefinite iteration of discrete closure across successive admissible units.
So if the wooden blocks suddenly turned into like puddles of water and merged together as you pointed at them, you couldn't say 1, 2, 3.
Exactly. The act of counting would fail because the distinction collapsed.
So counting doesn't create the discrete numbers? The discrete closure is what makes the act of counting mathematically possible in the first place?
Yes. Which is exactly why number constitutes the first foundational tier in Lilien's architecture.
It's blowing my mind a little bit.
It's not because ancient humans started scratching tally marks on bones before they drew geometry.
Right.
It's because number instantiates the strongest, most unyielding local regime of exact admissibility. It is the least mediated form of closure, requiring only exact distinction and lawful recurrence to exist.
So the ontological order runs from closure to number to counting.
Precisely.
Numbers aren't just primitive mental objects we invented to keep track of sheep. They are the unavoidable first consequence of closure stabilizing itself into a regime.
Right.
But here's the problem. The rigidity of digital bits or separate blocks eventually hits a wall.
It does?
If all you have is discrete succession, you just have a straight line stretching into infinity. 1, 2, 3, 4. Forever.
Right. It's very limiting.
What happens when we need those units to actually interact and combine?
Well, that boundary where succession is no longer enough forces an ordered extension into the second tier.
Rung 2.
Yes. We move from the regime of discrete closure to operational closure. We take the leap to algebra.
Okay, so in the discrete regime, the law was just succession, one thing after another. How does the law change in operational closure?
The decisive shift here is from succession to admissible composition.
Admissible composition.
Right. A regime achieves operational closure when its elements remain within the same structural identity under specified lawful operations.
Okay, so the elements are no longer just sitting next to each other in a line.
Exactly. They are being transformed, and the system must survive that transformation.
I want to make sure I'm visualizing this transformation correctly.
Let's hear it.
If I have a bucket of blue paint and a bucket of yellow paint, and I mix them, I get green paint.
Right.
Is that operational closure? Like the elements transformed, but it's still paint.
The paint analogy captures the idea of a combination resulting in a new state, but it misses a crucial structural requirement of algebra.
Which is?
Reversibility and exact conservation of identity.
Oh.
If you mix blue and yellow paint to get green, you can't easily unmix them to recover the exact original blue and yellow. The exact identity is muddied.
Okay, that makes sense. The paint is forever green. So a better mechanism would be something like a chemical reaction in a closed system.
Yes, exactly.
So I take hydrogen and oxygen and apply an operation like a spark.
Yeah.
I get water.
Right.
It's a profound transformation.
Yeah.
But the regime of the chemical system is completely preserved.
Exactly. The mass is conserved.
The underlying atomic identity is conserved. And with the right operation like electrolysis, I can perfectly reverse it and get the exact hydrogen and oxygen back.
The closed chemical system is a much more precise analogy. It perfectly highlights how identity evolves in this new regime.
Okay.
Because in arithmetic, identity is secured simply by distinction. This hydrogen atom is not that hydrogen atom.
Right.
But in algebra, identity must be preserved through transformation.
Through transformation.
Lilien defines this as operational identity. If an operation destroys the coherent identity of an element like mixing the paint into an irreversible muddy brown, the regime fails.
It breaks closure.
Exactly. Algebra demands that the element remains meaningfully situated within the lawful transformations of the whole system.
And this brings us to the concept of variables, which, let's be honest, is the exact moment in high school where millions of people decide they hate math.
Oh, absolutely.
The sudden appearance of letters, X, Y, Z. It feels like a massive loss of precision. Feels like the math is getting fuzzy.
It is so often perceived as a loss of rigor. But Lillian's framework reveals that variables are actually the ultimate proof that closure has upgraded its capacity.
Wait, how is a letter an upgrade in closure?
Because the operation itself, the law of composition, like addition or multiplication, has become so completely stabilized by closure that the law can now govern formally indeterminate placeholders.
Oh, wow.
A variable isn't a fuzzy lack of precision. It is an operationally admissible placeholder.
It's a container.
Yes. It demonstrates that closure has risen from governing particular isolated successions of numbers to governing general universal rules.
That makes so much sense.
Algebraic generality is possible strictly because operational closure governs the classes of admissible transformation, not just instance-by-instance arithmetic.
So when I write an equation like x plus y equals z, the x and y are basically the regime flexing its structural muscles.
That's a great way to put it.
It's a system saying, I am so incredibly stable under this specific operation of addition that it doesn't even matter which exact discrete units you drop in here, the closure will hold.
That is the absolute essence of operational closure. And the moment you introduce these stabilized operations, you naturally generate inversion, symmetry, and reversibility.
Like the electrolysis in the water.
Exactly. The ability to reverse an operation like division, reversing multiplication, strengthens the closure immensely.
Right.
The regime now preserves not only forward composition, but reversible lawfulness, yielding this deeply interconnected internal coherence.
So the formal symbols, the notations we memorize, are completely derivative. Algebra isn't the symbols. Algebra is the emergence of operations stable closure.
Spot on.
But just like the discrete bricks hit a wall, algebra hits a wall too.
It absolutely does.
Operational closure is phenomenal for finite combinations. We can add, multiply, divide, reverse our chemical reactions all day.
Right.
But what happens when we start dealing with infinity? What if we have a sequence that never stops, that just keeps approaching a limit forever? Algebra starts to break down.
It breaks down entirely. Operational closure only governs finite or rule-bound combinations.
Right.
But phenomena like continuity, boundary, convergence, and infinite extension, they cannot be reduced to finite algebraic composition.
It just doesn't compute.
Right. If a sequence of elements approaches a limit infinitely, algebra can describe the individual elements, but it completely lacks the structural grammar to articulate the infinite approach itself.
We need a new rule book for proximity and infinity,
Yes.
and that forces the next extension. Rung 3 of the architecture, relational and limit closure. From this, topology emerges.
Topology. The transition here requires a fundamental shift in the organizing principle.
Okay, from what to what?
We move from composition to adherence.
Adherence.
Yes. In the algebraic regime, admissibility was preserved under transformation. But in the topological regime, admissibility is preserved under limit formation, neighborhood structure, and boundary completion.
Wow. Okay.
Elements are no longer characterized solely by how they combine, but by how they are situated with respect to one another.
I'm trying to picture this shift.
Okay.
So, if you are walking through a city, navigating by landmarks, algebra tells you how many blocks you've walked. But topology is telling you whether you are fundamentally inside a neighborhood, outside of it, or standing exactly on the boundary line between two districts.
A physical map is a good starting point.
Right.
But let's look at something a little more relational, like a network of sensors or even a social network.
Go ahead, network.
In a topological space, exact distance doesn't matter as much as proximity and connection. Who is in whose neighborhood?
Right, who you're linked to.
Exactly. Lilien states that a regime exhibits relational closure when admissibility is preserved under relations of proximity, neighborhood, and approach.
And he heavily emphasizes the concept of adherence. What is the actual mechanism of adherence here?
Adherence means that an element is admissible strictly as a limit of other elements within a region.
Can you give me a visual for that?
Imagine a sequence of data points in a sensor network getting closer and closer to a destination coordinate.
Okay.
Relational closure completes a regime by demanding the inclusion of its limit points.
So it has to reach the end.
If a sequence infinitely approaches a limit, but that final limit point is excluded from the regime is broken.
It fails.
Yes. It fails to preserve admissibility under its own relational structure.
Okay, let's say you are building a bridge across a massive chasm.
Okay.
You build it halfway, then 3/4,
Yeah.
then 99% of the way. You are infinitely approaching the other side.
Right.
Limit closure says that the actual point of connection on the opposite cliff face must be included in your mathematical model. Otherwise, the entire concept of the bridge is incomplete.
Exactly. And the inclusion of that final point introduces a structural distinction that is completely absent in algebra.
What's that?
The strict mathematical distinction between an interior and a boundary.
Okay.
The interior consists of elements whose surrounding neighborhoods remain entirely tucked inside the region.
And the boundary is the literal interface where closure transitions between inclusion and exclusion.
Precisely. Every neighborhood around a boundary element intersects both the inside of the region and the outside.
So it's straddling the line.
Yes. The boundary isn't a defect or an edge you just fall off. It is a structural necessity of relational closure. It mediates the space.
And this mediation is what allows for the mathematical concept of continuity.
Right.
Now, usually continuity is explained with that rubber sheet analogy, right?
The classic topology analogy.
Right, you draw shapes on a rubber sheet, and as long as you can stretch and twist the sheet without tearing it, the topology is continuous. But that always felt a bit too, I don't know, physical to me.
It is very physical. Let's use a more structural mechanism.
Okay.
Think of a communication network where every node is connected to its immediate neighbors.
Okay.
A transformation is continuous if, after you upgrade or shift the entire network to a new server, the nodes that were neighbors before are still neighbors.
Oh, I see.
The overarching relational closure is preserved. If the shift suddenly isolates a node or forces it to connect to a completely different cluster,
You've torn the network.
exactly, you've violated the relational admissibility.
And Lilien points out that topology introduces this duality between openness and closure.
Yes, the open and closed sets.
Right. A closed set expresses completion under limits. It contains all the elements that adhere to it, including the boundary.
Correct.
But an open set expresses stability under local inclusion. Every element is safely in the interior without touching the boundary edge.
And they are dual expressions of the exact same relational closure.
Fascinating.
Topology emerges strictly when closure is extended from the operational stability of algebra to the relational stability of neighborhoods and limits. It answers the insufficiency of algebra when dealing with the infinite approach.
But topology has a massive limitation.
It does.
It only maps static relations.
Right.
It tells us where the nodes in the network are and who their neighbors are. It establishes the boundaries. But it tells us absolutely nothing about how data actually moves through those nodes.
It's just a map.
Exactly. For movement, for actual passage across the map, we need to step up to the fourth tier. We need transport closure, which generates geometry.
Geometry. The decisive shift here is from adherence to passage.
Passage.
Yes. In topology, closure governs where elements are situated. In geometry, closure governs how structure coherently moves, connects, and varies across a domain.
Lilien's definition here is really vital. He says, a regime exhibits transport closure when admissible structures remain coherent under lawful passage across a domain.
Yes.
And he stresses that this doesn't replace the topology, right? It sits on top of it.
Exactly.
Because you can't transport data coherently across a network unless the relational topology of the network is already built.
Geometry arises by deepening topology, not negating it.
Right.
Let's look at the primary transport law here, connection.
Connection.
Connection is the rule by which an admissible structure is coherently transported across neighboring regions.
Let me test an analogy for connection and also curvature.
I'd love to hear it.
Imagine you are transporting a highly sensitive spinning gyroscope across a landscape. The gyroscope maintains its orientation in space. The connection is the mechanical rule of the vehicle carrying it, ensuring the gyroscope doesn't just shatter when you move from one topological region to another.
Right.
It ensures that transport is lawful.
That is an excellent mechanistic analogy.
Hmm.
Transport closure requires that the passage preserves the admissible structure, the orientation of the gyroscope.
Right.
And once you establish the law of connection, you immediately expose the possibility of structured variation.
Because if I drive my gyroscope across a perfectly flat, featureless plane, its relative orientation to the ground stays exactly the same.
Yes.
But what if I drive it over a massive mountain range or across the curved surface of the Earth?
And that brings us to curvature.
Uh-huh.
Lilien defines curvature not as the shape of a drawn object, but as the structured deviation that occurs when transport closure depends non-trivially on the path taken.
So if I start at the equator and drive my gyroscope up to the North Pole,
Okay.
and you start at a completely different point on the equator and drive your gyroscope to the North Pole, when we meet, our gyroscopes will actually be pointing in different directions relative to each other, even though we both perfectly follow the rules of transport.
Exactly.
The fact that the path mattered proves that the underlying space is curved.
If transport were everywhere uniform and completely independent of the path taken, the domain would have no intrinsic deviation. It would be flat.
Right.
Curvature is simply the failure of transport to remain globally flat in a closure-preserving form.
This completely upends how we are taught geometry in middle school,
It really does.
because I grew up thinking geometry was entirely about protractors, rulers, calculating the area of a triangle, or finding the circumference of a circle. We are taught that geometry is the science of measurement.
And Lilien states that this educational approach is entirely backward.
Backward.
Measurement is derivative, not primitive. He establishes what he calls the priority of transport over measurement.
What does that mean?
It means before you can compare distances or measure angles or calculate magnitudes across a space, you must first have a coherent mathematical means of relating those separated regions.
Oh, wow.
You have to be able to transport your ruler from one side of the room to the other without the ruler's fundamental atomic structure scrambling.
If the universe lacked transport closure, moving a ruler would warp it unpredictably. Measurement would be completely impossible.
Exactly. Relation across a spatial domain is already a form of transport. Therefore, measurement presupposes transport closure.
Connection and curvature dictate the geometry long before a metric measurement is ever imposed on it.
Geometry binds local transport laws, how the vehicle moves millimeter by millimeter into global geometric coherence, ensuring the whole landscape doesn't irreducibly conflict.
But there is still one final insufficiency.
There is.
Geometry tells us how the vehicle transports the gyroscope across the curved landscape. But what if we need to regulate the exact microscopic split-second changes of the vehicle's speed and acceleration? What if we need to measure the infinitesimal friction of the tires at every single micro-moment of the journey? Transport closure cannot resolve variation at an infinite microscopic scale.
It can't. Transport closure governs the passage of form that is already stabilized. It cannot fully articulate the internal structure of continuous variation itself at an arbitrarily fine resolution.
Okay.
And crucially, it doesn't account for how those infinite microscopic changes accumulate into a cohesive global whole. For that, we must reach the absolute peak of the architecture.
Rung 5. Continuous completion closure. The pinnacle of analysis.
We shift here from passage to infinitesimal variation.
Okay.
In the regime of analysis, admissibility is preserved under infinitesimal transformation and is then completed through lawful accumulation across a domain.
In practical terms, for the listener, this is calculus, right?
It is. It is the generative ontological foundation of what we formalize as calculus.
Got it.
Analysis begins where variation can be resolved at an infinitesimal scale without destroying the system. This is what Lilien terms infinitesimal admissibility.
Meaning what, exactly?
If a variation was so small that it disrupted the admissibility of the regime, you could never have smooth change. Everything would be jagged and discontinuous at the microscopic level.
It would stutter.
Exactly. Analysis demands that change can be resolved at an arbitrarily fine scale while completely retaining structural integrity.
And this generates two massive structural expressions. The first is differentiation, which Lilien defines as the local law governing the infinitesimal variation of admissible form.
Right. Differentiation expresses the local micro-behavior of continuous completion closure.
So it's looking at the tiny details.
It ensures that local change, like the exact acceleration of your vehicle at a specific microsecond, proceeds under stable rules.
But local change isn't enough, right? We need the second expression, integration.
Yes.
The lawful accumulation of infinitesimal variations into a global admissible structure.
Differentiation gives you the exact rate of change at one tiny moment, but not the global map of the entire journey. When you accumulate that infinitesimal variation coherently across the entire domain, a global form emerges. Integration is the completion of that variation.
They're two halves of the same coin.
They are two halves of the same continuous completion closure.
So analysis is basically the ultimate high-definition resolution of mathematical closure. It takes the camera and zooms in infinitely.
It is the absolute peak of the resolution gradient. It extends the geometric passage of form by regulating arbitrarily small variations and locking them together globally.
And importantly, he introduces the concept of higher-order smoothness.
Yes.
Smoothness in this context meaning what exactly? Because I just picture a smooth surface.
It's more structural than that. If an infinitesimal variation is stable enough to undergo further infinitesimal variation,
Like a change of a change.
exactly, a change of a change, then higher order structure becomes mathematically admissible. This iterative stability is what generates true smoothness. Smoothness isn't just an independent, primitive visual quality. It is a higher resolution expression of closure, iteratively stabilizing itself across scales.
It's like a fractal of stability.
I love that phrase.
The closure holds all the way down to an infinite depth. So we are at the top of the ladder now. We've journeyed from the exact, discrete, digital bits of number
Right.
to the chemical conservation of algebra,
Yeah.
to the relational sensor networks of topology, to the transport pathways of geometry, all the way up to the infinite resolution fluid dynamics of analysis.
It's quite a climb.
It is, but standing at the top floor, we have to look down at the whole skyscraper and ask a really critical engineering question.
Which is?
How does this massive structure stay standing? Why doesn't the fluid dynamics of analysis just crush the discrete bricks at the bottom?
And that structural integrity is detailed in Section 7 of Lilien's work, The Architecture of Retention.
The architecture of retention.
He is emphatic that these 5 regimes do not just stand in a chronological sequence. They exist in a highly organized, systematic architectural relation.
They hold each other up.
The closure architecture is the ordered system by which distinct regimes are generated, linked, and integrated into one coherent mathematical whole.
The primary rule holding it together is the non-reduction principle.
Right. The non-reduction principle states that the framework absolutely refuses to collapse everything into one single monotonous domain.
Which would be monism, right?
Yes. And it equally refuses to treat them as disconnected, isolated silos, which is fragmentation.
Right.
A later regime in the architecture doesn't abolish an earlier one. It retains it and transforms it.
So, structural retention. Every later principal regime retains at least one essential structural moment of every earlier regime.
Exactly.
So if we walk back down the skyscraper, analysis retains geometry by using differential transport structure.
Yes.
Geometry retains topology by utilizing its boundaries and continuity. Topology retains algebra through equations and operational laws, and algebra retains the exact local separation of discrete number.
You cannot have the top without the bottom.
It creates this vertical dependence that is unbreakable.
It really does.
You know, it reminds me heavily of biological evolution.
Oh, how so?
Think about the human body. You have the highly resolved, continuously varying electrical signals of the conscious brain. That's analysis.
Okay, I follow.
But the brain completely relies on the circulatory system to transport blood across the body. That's geometry.
Right.
And the circulatory system relies on the exact boundary definitions of individual cellular walls to keep the blood from leaking out. That's topology.
Oh, this is brilliant.
The cells rely on the operational chemical conservation of proteins and DNA algebra. And all of that relies on the exact, discrete separation of individual atoms' number.
That is perfect.
You cannot have a conscious brain without the underlying discrete atoms. But a pile of atoms isn't a brain. Each level retains the structure of the lower level while extending it into a new regime of complexity.
That biological analogy beautifully captures the mechanics of structural retention and ordered extension. Each regime introduces a richer form of mediation while perfectly preserving the validity of the earlier modes.
It's so elegant.
And Lilien notes that alongside this vertical order, the ladder we just climbed, there is also a horizontal order.
Right. How does the horizontal order function?
The horizontal order manages the field of interactions at comparable levels.
Yep.
This is the mechanism that explains why we constantly see algebraic structures informing geometry or topological structures constraining analysis.
So they talk to each other on the same floor.
Exactly. The dual architectural order, the vertical dependence pulling upward, and the horizontal interaction stabilizing laterally ensures the global coherence of the entire mathematical universe.
And the boundaries between these regimes are not arbitrary. They are forced by the failure of the previous system.
Yes, driven by insufficiency.
Arithmetic became insufficient when we needed operational composition. Algebra failed when we needed limits. Topology failed when we needed transport. Geometry failed when we needed infinitesimal change. The latter is built out of necessary thresholds.
Which perfectly completes the foundational inversion we started with.
Right.
Mathematics is not a human invention of convenient tools. It is the structured, necessary realization of closure generating these regimes to resolve insufficiencies.
Which raises a profound historical question.
It definitely does.
If this generative architecture is so fundamental, if it's the very engine of reality, why didn't the great mathematical titans of the past centuries see it? Did they miss it entirely?
They didn't miss it, but they only saw it in fragments.
Fragments.
Yes. Lilien positions his work historically by showing how past foundational thinkers discovered partial localizations of this architecture. They found pieces of the engine, but assumed it was the whole machine.
Let's do a deep dive into a few of these historical titans because it really grounds Lilien's theory. First, Richard Dedekind in the late 19th century. He was obsessed with irrational numbers.
Dedekind represents the structural genesis of number. At the time, mathematicians knew about irrational numbers, but they lacked a rigorous foundation for the continuum of real numbers.
All right, it was shaky.
Dedekind constructed the real numbers via what we now call Dedekind cuts, effectively establishing number as a consequence of completion conditions on ordered sets.
Okay.
What he essentially discovered was number as a closure regime. He saw that completion acts as genesis, but his vision was restricted entirely to arithmetic.
He saw the first rung of the ladder and stopped.
Exactly.
Then we moved to Emmy Noether, an absolute titan of algebra in the early 20th century. Her work revolutionized both math and physics.
Oh, Noether's incredible. She generalized algebraic structures like rings and ideals through invariance and closure properties.
Right.
Her famous theorem linked mathematical symmetry to the physical laws of conservation. She explicitly formalized algebraic invariance, which is exactly what Lilien calls operational closure.
Because she understood that identity is conserved through transformation.
Yes. But again, her profound insight was confined to algebraic systems. She didn't extend that exact principle of closure to topology or analysis.
And then there's Alexander Grothendieck in the mid-20th century, who completely upended geometry.
Grothendieck is perhaps the closest large-scale precedent to Lilien. He completely reconstructed geometry from deep algebraic and sheaf-theoretic data.
What does that mean in this context?
He realized that the geometric space we see is actually a manifestation of deeper, hidden algebraic structures. He was looking at the horizontal and vertical retention between algebra and geometry.
Oh, I see.
But his monumental work remained focused on algebraic geometry rather than identifying a universal generator for all possible mathematical domains.
You know, it's like different teams of brilliant engineers crash landing on an alien planet and finding a piece of advanced hyperdimensional technology.
I like where this is going.
Dedekind's team finds the power core and says, this entire machine is a discrete battery. Noether's team finds the transformation matrix and says, no, it's a chemical refinery. Grothendieck's team finds the navigation system and says, it's a spatial transport drive. They were all brilliant, and their math was flawless, but their foundational insights were localized.
Exactly.
Lilien's meta-foundational framework takes the blinders off. He shows that all these geniuses were reverse engineering different modules of the exact same unified machine.
They were isolating discrete closure, operational closure, and transport closure. Lilien's contribution is stating that closure mathematics unifies them all. Closure is the single ontological source of the alien machine.
I really want to emphasize this point for you listening, because it is crucial to understanding the impact of Lilien's text. He is not proposing a replacement for set theory or category theory.
No, not at all.
He isn't telling mathematicians to throw out their textbooks or stop using their current tools.
Right.
He is providing an ontological reinterpretation that gives these formal languages a generative source. He is providing the profound why beneath the daily what?
Category theory, for instance, provides a miraculous language for describing interdomain coherence, how transformations map across structures.
Yeah.
But it is a descriptive language. It doesn't specify a generative principle from which the categories actually arise.
But closure mathematics does.
Closure mathematics provides that generative principle. Mathematical domains are differentiated regimes of closure. Their unity is generative, not just descriptive.
Which brings us to the ultimate distillation of this entire deep dive, Philip Lilien's master theorem.
The master theorem, it states. Closure is the generative principle of mathematics. Mathematical domains arise as differentiated regimes of closure, are organized through a coherent architectural structure, and are unified by closure as a single ontological source.
It's breathtaking. We started this dive looking at math as a messy, fragmented landscape of isolated islands, algebra here, topology there. But by diving deep into the concept of closure, we discovered the mountain range connecting them all. From the exact separation of a single digital bit to the chemical combinations of algebra, the relational boundaries of topology, the transport pathways of geometry, all the way up to the infinite resolution fluid dynamics of analysis.
It is one unified architectonic structure.
And it strongly implies that this structure doesn't just describe human mathematics, but the necessary emergence of logical form itself.
Absolutely.
Which leaves me with a final, slightly mind-expanding thought for you to ponder.
Yeah.
Something that isn't explicitly debated in Lilien's main text, but is a direct, unavoidable implication of everything we've just unpacked.
Let's hear it.
If mathematical domains, from discrete numbers all the way up to continuous analysis, aren't just arbitrary tools invented by human brains, but the necessary, inevitable unfolding of closure stabilizing itself, what does this imply about the structure of reality itself?
That is the ultimate question.
If we ever encounter an advanced alien intelligence thousands of light years away, their symbols will undoubtedly look completely alien to us. Their equations will be written in sensory languages we can't even fathom.
Of course.
But according to Lilien's architecture, they wouldn't have a choice in how their math is actually structured. They would have had to climb the exact same ladder of closure.
They'd have to.
They would have to mathematically discover discrete separation before they could find operational composition. They would need the relational boundaries of topology before they could build the transport systems of geometry.
Because the latter is necessary.
Exactly. Their math wouldn't just be translatable to ours. It would be born from the exact same generative engine, the exact same underwater mountain range.
It's incredible to think about.
Think about that the next time you balance a checkbook or just write down a simple number. You aren't just making a mark on a page. You are invoking the absolute baseline of the universe's architecture. You are stepping onto the first rung of a ladder that spans infinity.
The underlying engine of reality derived from a single principle.
Thanks for taking the deep dive with us.